We present Fisher Information Guidance for Learn Time-of-Flight Imaging.
3D imaging seeks to capture the 3D structure of scenes or objects, and has been widely used in many fields. It can be roughly divided into stereo vision, structured light, and time-of-flight imaging.
This paper focuses on indirect time-of-flight imaging, i.e. I2F imaging. Here is the process of I2F imaging. The light source emits a modulated signal to the scene, suppose as a sinusoid. The reflected signal is also a sinusoid, but its phase is shifted. We can derive the measurements from C1 to C4 by correlating the demodulation signal and the reflected signal. By calculating the phase shift, we can reconstruct the distance to the object. A traditional I2F imaging system consists of two parts, coding function and reconstruction algorithm. Over the years, a variety of coding functions have been designed, ranging from sinusoid to Hamilton functions. In the meantime, different depth reconstruction algorithms are proposed, from conventional method to the current learning-based algorithms. They have a common problem: these two parts are modified individually. Depth accuracy of I2F under low SNR is still quite limited.
To solve this problem, we propose to jointly optimize the physical implementable coding functions and reconstruction network.
However, there are two main problems that prevent the global convergence of joint optimization, i.e., the gradient vanishing problem and the large noise.
We propose to introduce the Fisher information as a guidance to help the global convergence. Fisher information is a metric of the amount of information included in the observation variables about the unknown parameters.
By deriving the Fisher information of the I2F imaging system and used as loss, we could realize high accuracy I2F imaging.
First of all, we formulate a differential forward model of the I2F imaging that considers the practical constraints. Firstly, since the bandwidth of coding functions are limited by the minimum bandwidth of I2F system, we formulate the coding functions with the summation of a set of sinusoids with different frequency.
Their amplitude and phase are unknown and learnable.
Secondly, the power of the light source is limited, we add the constraint of the maximum optical power, E. Thirdly, we add the positive constraint to coding function, which is physical implementable. Lastly, we calibrated the light falloff and add to the imaging model. Finally, we can generate the measurements from this model. Here we introduce the discriminative Fisher guidance, utilizing for guiding the learning of the coding functions.
Since we are targeting at large noise scenario, we approximate the noises of measurements with additive Gaussian noise of vary parameters.
Then, we could derive the Fisher information of the observed variable with respect to the unknown parameter depth z, p, from imaging model with noise. Besides, we introduce the discriminative metric to measure the difference and efficiency of different coding functions. Thus, the discriminative Fisher guidance is the summation of the Fisher information and discriminative metric.
We propose a dual-branch neural network to reconstruct the depth.
SEB is composed with a pyramid multiscale neural network, which could incorporate the spatial structure. PDRB is pixel-based depth extraction neural network, which could help the network to converge faster. For sufficient information fusion between the two branches, we introduce feature concatenation and attention-based fusion between the two branches.
The overall framework is shown.
With a differentiable physical imaging model, we obtain measurements of the scene and feed them into depth reconstruction network.
The fidelity loss and discriminative Fisher loss is introduced to guide the learning of the optimal codes. With this framework, the network and coding function are optimized.
To demonstrate the overall performance superiority, we compare our method with the existing I2F imaging methods, and our method enables to reconstruct depth of the lowest MAE across different noise levels.
3 different noisy scenarios are shown in figure and our method performs the best.
To further demonstrate the superiority of the learned coding functions, we compare ours with the other coding functions.
As the noise level increases, the improvement of the learned coding functions is large.
We demonstrate the efficiency of the proposed neural network with the existing TOF network. The reconstruction error of our network is lowest.
Ablation study of discriminative Fisher loss.
With the combination of two loss functions as discriminative Fisher loss, our method enables high depth precision and can greatly encourage the convergence in finding the optimal coding function.
We built a prototype system that can implement I2F imaging.
In physical experiments, we first capture images of the 3 books at different distances. As shown, the depth error of ours is the lowest. We further capture different scenes. The proposed method recovered the depth with much less noise effect and richer depth details.
Here is a brief conclusion of our method.
For the future work, we plan to work on the on-chip implementation and learn the coding functions under more complex scenarios.